So here we can start off with set theory. I guess this one's pretty easy, I think. I guess basically with this one, so they'll always tell you what the set is. And that's kind of like, there's a little symbol, so if they show like an S that is, but they'll probably tell you like what it is, or they'll say that like the numbers like 1 through 10 or something. And the set, that's just everything that's on it. And then empty set, this is the sign for an empty set. That's if there's nothing in it, like zero numbers or anything. I'll put like empty. And then I think the most important one to know is, and then this one, when there's a little bar above it, like we know, that's the complement. And then we have the N is the intersection. And the U is union. Okay, and what do you guys, can you tell me what's the difference between intersection and union? Which one's which?
Intersections both. It's like it appears in both, and then union appears in either one.
Right, exactly. So intersection is kind of like and both. And then this one, yeah, this one's either. I misspelled that, whoops. Or both too. And I like to remember that this is like a U, so it's like union, and this one's intersection, so it's kind of like and with an N. That's kind of a dumb way.
The middle of the Venn diagram.
Wait, is it both on both things?
Right, well, the union, this contains both, union can be both or. Actually, wait, sorry. You're right, yeah, so union, actually, no, sorry. Right, because union will have anything that's in both of them, or one of them, or one of the other. We can do a quick example, but intersection is only stuff that are in both sets. But the union is if something's in one set, if it's in the other set, or if it's in both sets. So anything in either of the sets, I guess. So I guess we can do a little example here. If we have a set that's like 1, 2, 3, 4, maybe 5. And then let's say we have set A. What was that? Let me just make sure that keeps recording. Okay, I think we're still in good shape. Okay, so if we have set A equals, let's say set A equals like 2 and 4, all the even numbers, what would A bar equal? What would be inside the set?
1, 3, 5.
Right, 1, 3, 5, because that's everything not an A. And then what about, I guess, and then if we have like B, if B is like 1, 2, 3, what would A and B be? And then what would A bar U be? Maybe we can just do these ones real quick. So I guess this one first, what would A and B? What would the intersection be of those two?
2.
Just 2, right? Because that's only numbers that are in both sets. So that's just 2. And then A union B. Oh, sorry, A bar union B, what would that be?
1,
1.
2, 3, 5.
Yeah, 2, 3, 5. Because remember, we're counting anyone that's either an A or B or in both. So that's the ones in there, the 2's in both. Wait, yeah, the ones in both of them, 2's in B, 3's in both, and 5's in A bar. So that would be that there. Do you guys have it? I feel like that's like all you need to know for that. I think we're pretty good on this, aren't we?
Yeah.
Okay, sweet. Then let's talk about combinatorics a little bit. Let's different colors. Okay. Okay, so this is like this is probably one of the more confusing things, I think. Well, I guess we can define first. So this is like when we're doing like N choose K and stuff. What's the difference between, let's get this down. What's the difference between a permutation and a combination?
The order is
Exactly.
permutation. Is it order matters and combination order doesn't matter?
Yeah, exactly. Nice job. So permutation, order matters. So that's kind of like he always made the example of like the Wheaties boxes, like permutations is like how many different ways can I rearrange these Wheaties boxes into a group, right? I can put one here and the other one there, or I can switch them around. Combination, you don't really care. You just say how many how many different groups of Wheaties boxes can I make with 20 if I'm picking 5 of them? So order, not matter. Okay, let's go over, do you guys remember what are the equations for these then, for permutation and combination?
It's n factorial over n minus r factorial.
Yep, and which one's that for?
The permutation,
Yep,
and then
N
Combination.
factorial Over n times
yep,
r thing. I don't know.
it's n factorial over r factorial times n minus r factorial.
yep, that's right. So that one's here, and then this one goes over here, n factorial minus, and minus r factorial and r factorial down here. And
There will always be more in a permutation than in
Yeah.
a combination.
exactly. Yeah, good observation. And we can, the formula kind of, that's when we can remember which formula is which, because if you stick an extra r factorial there, this number will always be smaller. So
What's r?
r is how many things you're picking out. It's like how many.
If it's n choose r.
Right, so n is, yeah, good point, Jerry. Let's define that. So n is like your total group that you can pick from. This would be like how many total Wheaties boxes you have. And then r is how many you pick.
Is there a way to write for a permutation? Like normally we write n big C R for a combination. Is there?
Yeah,
You just write like a P for permutation?
that's a good question.
I don't think we ever went over that.
I don't think we did, and I think it was on the exam too, wasn't it? There's like I think there was a question that kind of went over that.
Possibly.
Um,
I don't think we really needed to write like the actual exact way of writing it, but
yeah, I think, because I think you can do it with the C here, and I think with the permutation, I think you can do like P. And then you put like the N down here, I think. Like the R up there. We can double check that real quick. That's a good question. Let me look it up. I wish I knew on the top of my head. Yeah. Yeah, this, it shouldn't be in the exam. I think the most important thing would be to know the formulas, but I guess it'd be cool to know too, if like,
this one
yeah,
this one has n big P R.
it's saying like N for the permutation,
Permutation.
like N,
Or just like little n
I guess that'd be just the N.
and then a big P and then R. Yeah.
R, and then the other one has like a C, doesn't it? It's like C. So this one would be like a C. Looks like it's saying both ways here, where you have like your R down here and your N.
That's the way I've seen it.
Okay, yeah, so I guess that's the notation. Thanks for pointing that out. In case it's on the exam, but you should be good. If you guys, we know, if we know these things here, then we should be all set. And then we can maybe just practice we can just practice with the setup too, because that can sometimes, I feel like I always get tripped up on that. It's easy to get confused. So if we do a practice problem where it's like, so then, we always set these up here, right? Like, then when we do our problems, we always do like the double parentheses up here with the total on the bottom. So maybe we can just do a quick practice problem right now. So let's say we have like, let's say there's like 20 students in our class. And let's say there's 10 male and 10 female. And then let's say that there's like I don't know, like there's they just have like a student body or whatever, like they elect like a student council of like, let's say there's like 3 students on the council. But then all three of them are like girls. How would we find the probability of happening that? Like maybe we want to say like, hey, that's unfair to the guys, you just robbed them. How would we set this up to find the probability of this happening? Given that you have 20 students, 10 are male, 10 are female, how would you find the probability of getting like, you pick 3 from them and they're all girls? How would you, how would we set this up here? Because we have our three brackets. So I guess first question would be, is this a combination or permutation? If we're just worried about whether it's like a guy or a girl in council. Combination, right? Because it doesn't matter the order, right? It's not like they rank or anything. We just care about who's in this group. So how would we do this problem here?
Would we start upper left? Would we start 10 choose 3?
Nice. Yeah, so we can do 10 choose 3, right? We can count this as like the student council. There's 10 females to pick from. We're gonna choose 3 of them, and then what would go down here?
20 choose, or below would be 20 choose.
Yeah, 20 choose 3,
The other would be 10 choose 0.
10 choose 0, right? Like there's 10 dudes and you choose 0 of them, and there's 10 girls and you choose 3. And so then you would just plug in, we could write it out, but I feel like we feel pretty good on this, right? Then you would just do the N.
For each
And
one
then
of
it's
them.
R for each one of those. And one trick I always like to use, I always mess up these formulas, but you can always check if these 2 top numbers add up to this one and these 2 bottom ones add up to that one, you're probably good. Not always, like we could have still done it wrong, like, but if you ever check, I think it's always good just to double check, like, do these top 2 add up to that? Do these bottom 2 add up to that? And if they don't, you know you've set it up wrong, so you gotta switch something. If you do have it, if they do add the thing on the bottom, that doesn't necessarily mean you're right, but I feel like it's more likely you are. That's just one way to check that. So do we feel good on combinations, permutations? I feel like that's one of the more confusing things. But yeah. Okay. Now let's talk about this is an important concept too. Okay. I guess we'll go over here. I guess let's go over this real quick. Do we remember what the MN rule is?
Multiply them together.
Right, basically that, yeah.
Yeah.
I feel like it's kind of like, it's pretty intuitive, I think, how it is. I don't think you have to memorize what it's called, but that's basically where you, if independent events, you can just multiply them together. I'll just write this in shorthand, I guess, and I'm kind of slow at writing. Which is pretty intuitive. It's kind of like we did an example in class, I think, where it's like you have 6 shirts in your dresser and 5 like pants or whatever. And so if these are independent, like if we're just picking randomly, there's a total of, right, exactly, 30 outfits. And that's only if it's independent. If for some reason, like when you pick blue pants, you're more likely to pick if you're like colorblind and like you pick a blue pair of pants and so you're more likely to pick a blue shirt, then this wouldn't work, I don't think. But when it's just like random, like you're pulling like socks out of your drawer, it's dark out, you're just picking random, then we can just multiply them together. So I think pretty intuitive how it works. That's the MN rule. We're clear on it. Basically, if we're independent, we know that this is true. Conditional probability is just the same as probability of A. Intersection of A and B is just PA times PB. Also correlation 0, but I think we talked about that in the other one. If something's mutually exclusive, the intersection is going to be 0 and vice versa. If the intersection is 0, mutually exclusive. And the same thing here, collectively exhaustive. So the union of A and B is 1. So I guess an example here would be like A and A bar, those are mutually exclusive and collectively exhaustive, right? Because there's no box where both A and A bar are true. Either you're A or you're not. And so there's 0 intersection for that. And then, but they're also collectively exhaustive, right? Because the union, if we add up like the total probability of A and B, like all the A's plus the A's plus the A bars, like that just equals 1, right? You're either A or you're A bar. And there's no like A double bar or whatever, right? So these are collectively exhaustive as well. And then this is the formula I forgot in the other. So thanks for pointing that out, Parker. But yes, so if stuff's independent, we can find the intersection just by multiplying these 2 together. But if they're not, we'll have to use this formula to get it. So I guess jumping back to this, so independent, we know that A and B are not independent here, right? Because if this formula doesn't work, A and B is just 0.1. But if we try PA times PB, we multiply the 0.7 of B times the 0.3 probability of PA, then we just get 0.21. And as we can see, that does not equal 0.1. And so A and B are not independent. And so that's a way that you can, if they ask you if 2 things are independent on a test, that's probably the best way to do it. Multiply the probability of A times the probability of B. or you can multiply the probability of not being A times the probability of not being B. Whatever it is, and if any of these things don't equal multiplied together what's inside the box, like the intersection of A and B or A bar and B, then you know it's not independent. If any of these conditions don't, if for any of these boxes, it doesn't multiply and equal that, then it's not independent. So you don't have to disprove it once to know that it's not independent. Because if that's the case, then knowing something about B tells us something about probability of A. And so I think it's always nice to just draw out little boxes like that, because then you have your marginal probabilities here, and your little ones on the inside, your joint probabilities. And that will help us get the conditional ones. It can kind of tell us everything. And so I guess we can practice using this formula. So the probability of A union B is just this, right? Probability of A. So that's what, add those up. That's 0.3 plus probability of B. That's 0.7 minus probability of A and B. And that's to avoid double counting, right? Because with probability of A, we counted these two boxes. And with the probability of B, we counted these two boxes. But so we counted this box twice. So we have to minus it off. And it kind of works intuitively, right? If we wanted the probability of anything that has A or B, we could just add these three boxes, and that's just what we did, right? We added these two to these two, and then we subtracted that. And so then when we get what? Is that 0.9? Yeah. And so in a similar way, like, I guess the question that I brain farted on that was, how do we find the intersection if they're not independent? Well, then they'll give us something else. So maybe they'll say, maybe they'll say P, kind of like we calculated, AUB equals 0.9. Maybe they'll give us this in the problem, and then this will be empty, right? This is going to be what we're looking for. And then they'll do find. And then find the joint probability. Well, we would just do the same thing, right? P of A plus P of B is at 0.7 minus X, what we're looking for, equals 0.9. So then we can add that up, right? 1 minus X equals 0.9. Subtract that over there. Then we'll do 0.1 equals X. And so you can solve like that, and then we get 0.1. So while we're talking about this, let's talk about Bayes' law too. That's one of the important. This is probably like one of like the few. How's it going, Otto?
Peter?
Sorry, I think I was wrong on the time. I thought I was at 4, but it was at 3:30.
Oh, that's okay.
So we kind of jumped ahead. So sorry about that. But yeah. And then it's being recorded too, if that's cool with you.
Yeah.
Like, okay. Yeah. So this is like probably like this is one of like the few equations that you like need to know, and that's like super important. I guess can someone just like shout it out, whatever. Like what?
The P of A and B is over, or the probability of A given B.
Yep.
Is equal to the probability of A and B
Nice.
over B, over probability of B.
Nice. Over B. That's an important one to know here. And then like we said before, if something's independent, the probability of A given B is just A, but you can use Bayes' rule to it, and it will just cancel out to that, right? Like the probability of A. So that's that rule there. I think that's everything for like probability and combinatorics. Unless I'm forgetting anything. Is there any last? Do we have any questions on that or? Okay.
Most of it.
Yeah. Okay, we can touch this real quick. Where I think we worked a lot with these. I think we probably feel good, but basically, like, do we feel good doing like these, like when they make us do like the double integrals? I feel like we got like a lot of practice doing that later in the course too. So I feel like it's probably
Like the math of it.
easy. Yeah, like the math and like the setup. Like, I guess like this is like these are always like these are pretty simple. Like you just integrate first with respect to X and then with respect to Y. So it shouldn't be too crazy. I feel like we're good on that.
The
Yeah.
the math behind it, like the concepts still like are. I'm trying to have it click. So when you double integrate, that means
Yeah.
the collective probability within that range. So if it was right, or so if the total range was 0 to 1 and 0 to 1, that should equal 1, right?
Like when you integrate it.
Yeah.
Right, yeah, if this is like a distribution function, yeah. like the total will always integrate to one, because that's kind of like the thing where it's like the total probability always has to equal one for everything.
And then if it's just one integration, then you're just looking for just the probability of X or Y
Right,
in a certain subset of
exactly.
the others.
That's the marginal distribution.
Yeah, exactly. Yeah, so if this is like our joint here, right, if we integrate out the X, then it'll turn into Y, and then if we integrate out the Y, it'll turn into the probability of X. So yeah, those are pretty easy. You just integrate one then the other. And I think the other thing too is that, I'm pretty sure this is right, but I think the inside integral, that this corresponds to like whatever is inside of the dx dy. So that, like, if this was like different for any reason, usually they'll clarify in the problem too, to not make it confusing, but like, if we had this, then that would mean the range of X is from 0 to 1. And then the range of Y would be that 0 to 2, but usually you'll just say in the problem to make it more clear, but I'm pretty sure that's right.
Now, the next part, I remember there's a homework problem where they combined Bayes' law and the integration.
Yeah,
That threw me off. I still don't understand the intuition behind it.
is that like, yeah, I think that's kind of like, I think that's a little bit more like content from like exam 2, when we're doing continuous stuff. We can go over it real quick if you guys want to.
But this is for the final, right?
Yeah, we can go over that too then. I guess the idea of that, because that's kind of the idea of like the continuous conditional distributions, right?
Okay.
I guess we could just like integrate this out real quick.
Well, you're saying it'll be covered in the next,
It should be covered in the next video.
I'll grill them with those questions. I'll.
Okay, but no, we can just go over it like super quick. I think the idea with that is that you take like your joint, kind of like this, and then you take your marginal of B.
Bayes' law.
Right, that's like the Bayes law, and then you can just integrate that for whatever range you
All
want.
that.
Uh-huh,
Oh, well.
and that will give you the probability you want. Yes, that's kind of the thing. So yeah, that's like how we do like the continuous conditional functions and the other one.
Do you double integrate it or just integrate?
I think you integrate with respect to, I guess in this case it would be, you would integrate with respect to A, and then you would just plug in a value for B. Like, once you do the integration, because we're saying that,
Given that B is equal to something.
right, we're saying like the probability of A given B. So we'd have our joint up here, and then we would just plug in the value of B that we have for all our B's in there.
Okay.
Yeah, it's a great question. Let's talk about that too, because that's a perfect segue into this. So, I guess we're all pretty good at this now, but let's just define this too, super easy. So let's just define joint, conditional, and marginal distributions. And we already kind of did that, but can we just like shout out definitions
Definition of
all these different types of probabilities? So I guess joint, that's just like of both of them happening at the same time, right? So I'll just put like, well, like, maybe, I guess the best definition, this would be like a combination of both. That's the best definition of both. And then what about conditional? I guess we already talked about it. Conditional is just like, that's like the Bayes, right? That's like the probability of A, given that we already know something. That's kind of like the Bayes law thing, right? Like, given that X is equal to 20, what's the probability of Y? And we can run an example here on the board real quick. And then marginal, that's just the total probability for each one, right? We're not even caring about the other break. Or like total I'll just say total prob distribution for each one. I don't even know why I'm writing that. Let's do a quick example. I think that will help more. I think this was like on the homework problems or something. I guess it's just like a class example. So let's say we have this one where it's like X can either equal 10 or 30. And Y can maybe equal 10, 20, or 30. And then I'm just gonna make up like random probabilities. 0.1, let's make that 0.2, 0.2, 2, and 0.2. Does that add up to 1? Yeah. Okay, so I guess this would be like, so if this is like this is just like a random example distribution, but these are all joint probabilities, right? Like the probability of X being 10 and Y being 10 is 0.1. The probability of X being 30 and Y being 20 is 0.2. And so that's joint. Anytime you're talking about both of them happening at the same time and the combination of it, that's joint. And one of the big rules of probability is that probabilities always have to add up to 1, like your total probability. And so I think there's an exam where it like added up to like something else or whatever, but it should always add up to 1. And then I guess Conditional, that would be like if we're saying like, what's the probability of y being equal to 20, given that we already know that x equals 10? And so,
33.
right, exactly. Or I think it might be a quarter. What did I say, 20 given that x equals 10? I forget what I said. Yeah, so I guess then we would
Oh,
use.
yeah, it'd be a quarter.
Right, because then we would use like we already know that x equals 10, so these are the only options. And so the new total probability is like 0.4 out of this, if that makes sense. And so 0.1 is just a quarter of that, and that's the same as Bayes' law, right? A and B, 0.1 over the probability of B, and that's 0.4. And so when we add up the columns like this, kind of like we said, for all these inside numbers have to add up to 1. And then these, when we add up the rows and columns, these need to add up to 1 too, because these are the marginals, right? If we don't care anything about what x equals, this is the marginal probability of y, right? It's 0.3 that y is 10, it's 0.3 that y is 20, and it's 0.4 that. And so, and the same with x, that's the marginal for that. And so, this should be pretty easy. It's marginal, just add them up. Joint is the combo of both. And then conditional is just the probability of like y being something, given that x is the other. And conditional, we're always going to want to use Bayes' law for that. So I think we feel pretty good on that, right? No additional questions and stuff. Okay. Let me just look at my paper. Yeah, now let's talk more about, let me just make sure this will fall. It's still in the recording. I think it should be. Yeah, maybe we'll move over here to have more space, if that's cool. Now let's talk about random variables. I guess what would be like a good definition we could say for a random variable if it said it on a test?
Chosen at random.
Was that
Chosen at
it's
random.
chosen at random? That's perfect. Like that's just like, it's like if you roll a dice, you flip a coin, like you really don't know what it equals. It can equal whatever, right? Like if I roll like a 6-sided dice or whatever, I might get a 2, then I'll roll it again and get a 3, I might get a 4. It's not like it's gonna be different every time. It's gonna be random what value you get every time. So and so that's kind of like, I guess that kind of plays into like the whole idea of like expected value and variance of things, right? Because we can't always be sure of everything. And so that's why we always use that. And so now let's talk about expected value and variance. So this kind of has to do with like the random variable. So expected value, that's just kind of like the mean or whatever. The expected value of any x, like that will just equal like the mean, or mu as we say, right? And we get that, the notation's kind of weird, but like we would just add up like every x times the probability of x if we wanted that. And so I guess it's all the way down there, but I guess I can yeah, I shouldn't have done that. But I guess like the expected value of this, you would say the expected value of y, you do 10 times 0.3 plus 20 times 0.3 plus 30 times 0.4. And what that gives you is the expected value, it's like a weighted average. I think a lot of times when we think of average, we think of just add up all the numbers together and divide by 3 or whatever. And that can be the expected value, but only if it's of equal probability. Like if you're doing coin flips and stuff, you can do that. But here that would mess you up because you're more likely to get 30 than you are to get 20 and 10 as your value. And so that's going to pull that weighted average back toward, it's going to pull it closer to 30 than if you just average them. So that's kind of the idea of that. Like the mean is just kind of like the weighted average. It's not necessarily what you get every single time, but it's what you expect to get. And so let's talk about some of the properties of the mean, I guess. So if we have like expected value, my bad. So if we have like expected value of a constant, I'll just call it like, let's just use like 50. That's just going to equal like 50, right? Like that's obvious. I guess that will always be the same. Like the expected value of a $20 bill is just $20. Like that's pretty easy. And then expected value of x is just mu. We kind of established that too. And then if we have like the expected value of 50x, then we can always pull brackets out of these constants, or out of the, so we can pull the constants out of the brackets. And so if we have a problem like this, we have to evaluate, then we would just get 50 times expected value of x, which is the same as 50 mu. And so that's the nice thing about expected values. You can pull constants out and stuff. And then what if we have something like this? Like, let's see, if we have like, I guess here, I'll ask you guys here, well, how would we, how could we evaluate something like this if it's like expected value of something plus something?
You could separate them.
Nice,
Expected values to be expected value 50x and expected value of 13.
nice.
And then it'd be the same, we already found the 50x one. And then the 13 would just be, it just equal 13.
Sweet, exactly. And so, yeah, you can break them up and find the expected value of each thing being added together, and then you would just get whatever that is, right? That's 50 mu plus 13. And so those are kind of the properties for that. I think that's all the ones for expected value. Nothing too crazy. And then now let's talk about variance. I guess first, what's the equation for variance? That's an important one to know too, I guess.
Expected value of our x minus the mu.
Okay, yeah.
And then squared. Or there's another notation.
So I think this one we have to like,
Summation.
right, we have to sum this one up. I forget if the sum's like on the inside or the outside. I think it would be that. Like you would add up yeah, that's one way to do it. You can add up every single x minus mu squared. And then what's the other way? What's like the shortcut, I guess?
The e of the expected value of x squared.
Nice.
Is the other way it's squared.
Yeah. Yeah, so here, that first way you said it, like, that's totally valid, but I'll just write it this way too, because I guess it's like a shortcut or whatever. So that's our other question, right? E of x squared minus mu squared minus e of x squared, or we can write it this way too, I guess. Right, and it's important to notice, like, I guess the only important thing with this formula is like, this one, you're taking the expected value of each x squared variable, and this one you're taking like you're squaring like the expected value. So I think you guys all know this. I'll just do it for the sake of the video, I guess, but like e of x squared, it's not the exact same thing, because e of x squared, like here we would find the expected value of y, which is, I don't know what it is, like it's like 20 maybe, I don't think it is, and we would just square that and we'd get 400. That would be like the e of x. But the e of x squared is we would square everything. We would square all these values here and then multiply them by their respective probabilities. And that's not the same thing, right? Because 30, this is going to get bigger by a factor of 30. Well, that's only going to get, so these are going to get like way bigger, and those are going to get kind of bigger, and that's going to skew things. And so, yeah, so that's kind of the idea of this. Like, we're going to square everything and multiply it by its probability of happening and add it up. And then we're going to subtract the expected value of it squared. Okay, let's talk about some of the properties of x then. Let's say if we have the variance of a constant, or I guess we can I guess I'll just draw this out real quick to maybe build some intuition. Kind of like I should have just done it back before, because that was really good what you said, Otho, that like, I guess variance, what we're measuring is we're measuring how often stuff deviates from the mean, right? And so if this is like our mu, let's say we're like rolling like a dice, and our mu, I think the mu of a dice is like 3.5 or whatever. And then we get like a few rolls down here, we get like a few like threes and like a 4, and then like a couple 6s and like a 1. I guess then we can measure the variance, right? We would find how far each roll is from the mean, and then we would square that. And so if you get a lot of values often that are far from your mean, you're gonna have a high variance. And if you get a lot of values that are close to your mean, you're gonna have a lower variance. So it kind of measures like the variability and things. So variance of a constant, that's just a constant, right? Or that's just 0. Like 50 is never going to vary from 50. And so the variance of a constant is always 0. And then what if we have, so then I guess, so then variance of x is just like v of x. What if we have variance of like 50x? How could we evaluate this one here? If we have a constant inside of there?
We square it.
Exactly. So kind of like up here, we can just pull out constants. Variance is the same, except since we're like squaring since we're squaring things with variance, we're squaring how far things are from the mean. We're always gonna square things when we do things with variance. So we're gonna pull that guy out there, and then we can evaluate that. It'd be 50 squared times v of x. And then assuming we know what our x is, we could calculate that and solve for that. And then I guess the last one, what if we have like, variance, kind of like we did up here, I guess, variance of 50x plus 13. How could we go about this here? What would it equal and everything?
You could take away the 13.
Right, you can just take away this, I guess kind of like how with expected value, you can with variance, like you can just break it up. So we could get, you're right, variance of 50x plus variance of 13. And like Otha said, we can, this will just go to 0 because that's a constant. And then we get like variance of 50x. And that's just the same thing as there before.
And then when you do plus 13, it's just like plus 0 because it won't matter.
Exactly, yeah.
When you do like, if you did variance of 50x plus 13x,
Uh-huh.
I guess you could just add those together. But when's the one when you have to, I guess would it be 13y if you had to do the covariance? The
Right,
2AB
Yeah,
covariance, okay.
that's the variance thing. I think that's stuff that's like on the next exam, I'm pretty sure.
Okay.
Adding it together. But yeah, so yeah, whenever we're doing like one variable, it's pretty easy. But yeah, then when we're adding like the variance of like two different populations, then we can do that formula of like the, when we square them and then minus the 2AB covariance. So I think we probably feel pretty good on this, right? I don't think there's any other questions. Then I guess, oh, then it looks like we have to go over this too. Bernoulli distributions, these ones are pretty easy. This is just like, I guess it's like, that's like if it's binary, I guess. So that's a Bernoulli thing. Like a coin flip or something, like it's either heads or tails, or like a game, I guess, like you either win or you lose a game, assuming you can't tie if there's like overtimes and stuff. So Bernoulli distributions are like binary, there can only be one thing or another. And then what's the, I guess, what would the expected value? And so if we say binary, we can just draw a little distribution here. We'll do a quick example. Let's say that like the probability of winning is like equals P, and the probability of lose equals, well, I guess what would that be? Well, it'd be P. Or sorry, no, it'd be 1 minus P. How would we find I guess, how could we, for a Bernoulli distribution, what would the probability of, what would be the expected value of our, what would be the expected value of our x if x is distributed like this?
You would do would you just replace winning with 1 and losing with 0? Is that valid?
Exactly, yeah. And so I guess we can, right, yeah, like, I guess, yeah, I should have clarified that, like win equals 1, if that, and win, and the probability of like losing win equals 0 is that. And so if you kind of do that thing where you like add the probabilities time, that you'll get P times 1 plus 1 minus P times the probability of, or times like the value of losing, I guess, which is 0. And so you would just get E. And so that's the expected value of like coin flips and stuff like that is just P. And then the variance is a nice shortcut too, where for Bernoulli's, this one's kind of nice because it's a little bit, like you can do this formula and it works for Bernoulli's, but it's kind of nice because you can just do this little formula and it's like a cheat sheet. So P and then,
Where does that
and so that's the
Come
variance
from.
of any Bernoulli thing there.
where does that equation come from? Is there like a proof behind it, or is that something we accept?
I think it's just something we accept. I forget. I don't know the proof, but I know that if you do like, if you can do this equation with the Bernoulli, like you can, I don't know where the proof comes from, but I think you just like do this equation and it like works out.
Okay.
But this is like a simpler way. Yeah, sorry. Well, right, because I think E of x squared, that's like P squared. And then that's, well, I don't know. Maybe that can be for another day. But yeah, I think it's like when you plug in the Bernoulli stuff into that, like it comes out pretty easily. So I
Okay.
think it's like kind of basically the same thing. So that's that. Then we can talk about. So I think that's everything we have to go over now. And then we can just talk about variant or covariance and correlation real quick.
Definitely.
And then I think we'll be all good for this stuff at least, and then they'll cover the other stuff. I don't have a lot of room left on the board. We can maybe just,
Are you scared of erasing it?
yeah, I can, yeah, I mean, I probably could erase it.
It's like the set theory stuff, probably.
Yeah, okay, that's a good idea. Okay. Yeah, so let's talk about covariance and,
Or you can write over the other stuff, but at an angle so you can tell the.
like,
I heard of stories of people doing that and it's just, yeah, it's funny. Okay.
that would be pretty cool to do that. Okay, let's do, yeah, so let's talk about covariance. So covariance in correlation, that's when we want to measure like how much two variables move together. Okay, what's the equation for this one then? You want to shout it out, or we can,
I know Arthur knows.
I'm sure you guys know it, but what's that?
I know Arthur.
No, it took a minute. It's the x minus mu and then y minus mu.
Exactly. Yeah, so this is kind of where it comes from. I guess we could, well, yeah, maybe let's draw a little graph of that. That's a good idea. I like to build a little bit of intuition. So say we have like, I don't know, if we have like weight and like height of people in the classroom. And let's say like this is our, let's make height our x and weight be our y. And so this will be like our mu of x, right? This is the average height. Maybe it's like, let's say it's like 5, I don't know what it is, like 5'8" maybe, or 5'6", I don't know. And mu y, maybe that's like, I mean, I don't know what that would be. They're like 170. I have no idea. But let's say we took like the whole class and we just like plotted like all their weights like here, then we would get like, there would be a mu of x and a mu of y, right? And that's kind of like that point there. And covariance kind of measures like how much x varies with like a variance in y. And so I guess kind of like Otto said, to find the covariance, we would do I think you do 1 minus n if this is the case, I think. So you would do for each observation, you would find how far it is from the mu of x and multiply that by how far it is from the y. And that's kind of like the example. I guess I drew kind of a dumb graph here, but that's kind of the same. It's kind of the same type of thing, right? Where we're squaring the distance. This is the same idea where instead of squaring, we're just gonna multiply the distance by 2 generations. So say we have like, maybe there's like 5 kids in the class and like one of them's up here. He's kind of big and like heavy. One of them's like here, he's small. And one of them's like really short, but like a little bit fat. And so to find like the covariance of the height and the weight to measure like how much they're going together, we would take each little observation like this. We would take the x of that guy and the y, how far him is. Then we would take that y and that x. Then we would find this distance here, this x times this y, and then we would multiply all those together and then divide by n. Add them all up and then divide by n. Because that makes sure that if you add like 100 observations, it doesn't like make it bigger just depending on observation. So that's like, I guess it's kind of an ugly graph, but that's some of the intuition behind covariance. And there's that equation. I'm going to erase this equation because the nice thing is we can just use this one. There's a, oh shoot, well.
In x times y
Nice.
minus e of x times e of y.
Yeah, nice. And there's like a proof for it and everything. It's pretty easy. I don't think we need to cover it. It shouldn't, well, we could go over it real quick maybe. But kind of like the same thing how with this equation, it's like the x squared is not the same as the x squared. E of xy is not the same as e of xy unless it's independent. This is kind of nice because then if something's independent, we know that the covariance will just be 0. Exactly, because they don't correlate at all. They don't move with each other. Like being heavier does not influence you. If this is a positive covariance, that will mean like being heavier means you're more likely to be taller. And so for independent things, that's just 0. But kind of like that, like if we were like trying to find the covariance of this thing, like y and x, whatever that is, we would multiply these two together, right? 10 times 10, multiply it by the probability, and then multiply 10 times 20 and find the probability of that. So that's our e of xy, right? We multiply x times y, find the probability of that, and then the e of x and e of y are just the same. So that's that. And then I guess, what does covariance tell us? Like what can we learn? I guess if we get a covariance that's positive, what does that tell us? Well, I guess it doesn't tell us that much. Let's say, so what if we run this, if we get a covariance of like positive like 686,000? What is that? That really doesn't tell us all that much. The problem with covariance is that it doesn't scale things because it depends on the units, right? We might be measuring height in like millimeters. And if we measure height in like in miles, then each of these X values is going to be really small. And when we do that, we're going to get something like really small. But maybe the scientist is like really precise, or maybe they're British and they measure into like millimeters. Then like this guy's gonna be like what? Like they'd be like 2,000 millimeters. And then you're multiplying 2,000 times like maybe you're measuring in grams the weight. You're measuring 2,000 times 18,000, and you're gonna get a huge covariance. You could get a covariance of like this, but that doesn't necessarily mean that it's like that they're like strongly correlated, right? Because that's the big problem with covariance, is because it depends entirely on the units we use. But the two things it does, the three things I guess it does tell us is that it tells us at least what type. It doesn't tell us the strength, but it tells us what type of correlation. So if we get, I'm going to erase this. So if we get a positive, we know that they're positively linearly. Well, I'm not even going to write it out. That's dumb. But we know that we can learn three things. So we can learn if they're positively linearly correlated, right? If we get a covariance that's bigger than 0, we know that generally being heavier means that you can expect someone to be taller. And that's the same thing too. If we get a negative covariance of like, we don't really know how strong the thing is, but we know that generally, that would mean that generally heavier people are, would that be that heavier people are kind of like shorter, right? That would be like if we have like a downward sloping line, kind of, it looks like that. And a positive correlation would be something like that, right? Like they kind of move together. And then if it's 0, that just tells us that they're independent, or that there's no linear correlation. That doesn't mean that they're not related necessarily, but it does mean that they don't have a linear relationship, at least. That's what covariance measures. And I guess it shouldn't be in the exam, but there's kind of like this example I think we did in class once, where it's like, you can have like age and like how much dollars you make. When you're a baby, you make nothing. Then you go to school, you start making more money. Then you're making bank. And then you like start retiring and you make no money. And so obviously there's a correlation, right? Like how much money you make does depend on your age. But if you sometimes like with certain things, like maybe we would get a covariance of 0. Like if we ran the numbers, maybe we would just get like a linear line like that through it.
Its correlation's parabolic.
Exactly, right. It's a parabolic thing. And that's the only bad thing about covariance and correlation, that it only tells you about like the linear strength. And I guess it's the same thing too. Like you can get a correlation of 0. Well, let's go over that in a sec, actually. So I'm going to erase that. Well, here, I'll just put that up here. It tells us if it's plus, minus, or 0. Those are like the important things. But now let's talk about correlation. Because before we were kind of saying that like the problem with covariance is that it doesn't really tell us anything. Correlation tells us, the nice thing about correlation is that it scales everything. So it gives us like a set number. So the nice thing about correlation is it always falls in this domain. It has to be between -1 and 1. If you get a correlation that's outside of that range, you've done your math wrong and you should do it again. And so you can shout out, what's like the equation, I guess, for correlation coefficient? Sometimes I write it with like a little like.
It's a covariance over the standard deviation of X, standard deviation Y.
Nice. And yep. And so the standard deviation, that's just the square root of the variance of X and the square. So this is how you calculate it here. I guess we all know these problems get kind of nasty and long because you have to find E of X squared, then you have to find the E of X, then you have to find like E of XY. These ones get pretty long to do, but this is like our formula here. And what this does is that this, kind of like we were saying before, like if we're measuring height in millimeters, we're going to get a huge covariance. But the variance is also going to be big because the distances, we're squaring them, and those are going to be big. And so these variances, they serve to like scale our covariance and spit out like a number. And so basically the thing with, this is getting kind of ugly. But basically the thing that covariance tells us is it tells us the same thing, or sorry, correlation, it tells us the same thing as covariance. It tells us if we have a positive, negative, or 0 linear correlation, but it also tells us the strength. And so the closer we are with covariance to 1, I guess like the more stronger it is, right? And closer to 0, that's kind of like a weak thing. So I don't know like the specific numbers, but basically like if we found the covariance of this and we got like the correlation, I keep getting confused. I guess if we got like a correlation from this that was like, I don't know, like 0.07, what would that tell us about the relationship between height and weight? Like direction, strength, what would that tell us?
There's not much. There,
Right.
width doesn't indicate height or the opposite.
Yeah, right. That means it's like technically there's a small, like technically they kind of move together, but that's really not all that strong at all. Like 0.07, like I mean, it's nothing. But on the other hand, if we did something like this, like if we did like that and got like, I don't know, like 0.97, what would that tell us? Like
Pretty strong.
that means that would be a pretty strong correlation. That would look something like this if you had like data points like that, like. I guess we could draw it out real quick, but kind of like strong correlations kind of look like this. That would be like a strong positive. A strong negative would look like this, like they move in a line. And then I guess weak positive would be something like this, where it's like they kind of move together, but.
So the correlation doesn't mean the slope, it means how scattered it is from the line.
Exactly. That's a really good way to put it, right? It just measures like, yeah. I like that. Yeah. Yeah, because it's not necessarily the slope, because you could get like. You could get something like this.
You could get a slope of 1, even if the dots are not.
Right, exactly. Yeah, that's a perfect way to put it, right? Because maybe we have like a correlation like this where it's like.
The line of best fit could be 1.
Exactly, yeah. The line of best fit would be like 1, but the correlation would be pretty low because it's like if I know X, like it really doesn't tell me that much about Y. And so that's kind of the nice thing about correlation though, is that I guess one of the things too is like correlation, we can use it to find like if we have a pretty strong correlation, we can use it to make useful like predictions. So it won't necessarily be the case, but in our example, let's say we have a correlation of 0.7, and then we have like then we can make a line of best fit with it and everything, and then we can then if we know like the height of a kid, like we can get a pretty good estimate of like what their weight would be. Like not necessarily, but we know that like if a kid's shorter than the average, they'll probably be a little bit lighter than average too. And so that's like, it's not always like an exact prediction, but we can like covariance, it is, or correlation, sorry, it is useful for prediction. So that's kind of the big difference. Like covariance really only tells us the direction of the relationship, and correlation is kind of like squared. And so that's the big thing. And then I think the last big point with this is that I think, correct me if I'm wrong, but I think if independent, then your correlation is 0. But if your correlation equals 0, that does not necessarily mean that you're independent. This is one of those like, this is like a pretty good trap, I feel like, that a professor could do in an exam, right? Because if your thing's independent, you're gonna have a covariance of 0 and you're gonna have a correlation of 0. Like if there's no relation between X and Y, there is no linear relation. But kind of like we said here with the example of like age and earnings, like just because we get a covariance of 0 maybe with this, that doesn't necessarily mean that they're independent, because knowing something about X, that tells you a whole lot about Y. If someone's 99 years old, like we can pretty accurately predict their earnings. And if they're like 2 years old, like we can really accurately predict their earnings. So those X and Y are not, they're not linearly related. It's a parabolic thing, like we said before, but they're not independent, because knowing about X tells us something about Y. So I think that's everything for covariance. I think that's everything we have to cover. Was there anything I forgot, you guys think, or any other questions you have, or?
Pretty good.
Okay. Yeah, I think you had the one question right about if it's, I forget what it was. It was if they're not independent, how we find the union. What was that? That was our question, right?
It was just like if they're not independent, probability of A and B would equal the probability of A times the probability of B minus the probability of A union B,
Yeah.
which I thought was one of our.
Wait, no, you're right. Yeah, sorry, I totally forgot this one formula. Yeah, because you're right, because I guess the probability of A union B.
Oh, it's probability of A union B equals A, probability of A plus probability of B minus probability of A and B.
Okay, that's what it is, yeah. Sorry, I totally blanked on that. I forgot about that formula. Okay, so yeah, thanks for pointing that out. Yeah, so I think, yeah, so that's the way you could find the
You can
intersection,
rewrite
right? You
that.
could like algebra it out and put that over there, and then you pull that. So yeah, you were right. My bad. I was wrong about that. So thanks for pointing that out. Do we have any other questions or anything? Or we could do some practice problems if you want. We could just end too. Whatever you guys want. I know you probably have to finish that homework up, right?
Gotta go. Are there practice problems on Learning Suite?
There's for this stuff.
Or is it just like the stuff from the first unit?
Yeah, I guess practice problems, like you could go over old homework problems. We'll try to get, because we've been writing, like Dr. Price has been making us like write problems throughout the semester.
Mhm.
And so we can see if we can release some of those, or maybe we can make like a fresh practice test with some of that.
That'll be
That'd
awesome.
be good. And another classic too, I feel like we all probably do it, but I always like just asking that to you, like, hey, give me like 6 problems where I have to calculate the covariance.
That's a good idea.
That always works pretty good. Sometimes they make mistakes, but a lot of times it will be pretty good because they can just give you like whatever type of problem you want. And then you can have them check your answers and stuff. So that's always good too, but it's always nice to have like a good practice test. So that's. Right, so we talked a lot about correlation. I guess the thing I forgot to talk about, so correlation does not equal causation. It's kind of like the classic example, like in the summertime, ice cream sales go up and like homicides and murders and crime rates go up too. But it's not like eating ice cream doesn't cause more murders, right? It's more just like it's summertime, it's hot out, people eat more ice cream, they also do more crimes for whatever reason. So that's a correlation, which is pretty strong. Like the more ice cream sales there are nationally, whatever, the more crimes there are too, but it has absolutely nothing to do with each other. And so we can use correlation as a prediction. Like if we see that there's like ton of ice cream sales in July, we can use it to make a general prediction like, okay, there might be a little bit more crime this month. We can do that, but we can't say we can't necessarily say that ice cream is causing all the crime. The correlation, they're moving together, but they're not causing each other, if that makes sense. And then I think they asked about this formula, and I said it was gonna be another review, but I'll just go over it because I guess it is in this unit. This is definitely a good one to know for the exam. But apparently you can be a TA without knowing it because I totally forgot about it. Well, I mean, I forgot how to do it. I forgot what it was. And so that's just our last like variance property. Sorry for not writing it down with the other ones, but when we're adding like the variances of 2 different variables together, we're gonna use this formula. And so we're gonna kind of the same thing. We're gonna square that, square the constants, pull them out, and then add 2 times the constant on both the variance on both x and y times the covariance. And so the nice thing about this is I guess it works kind of intuitively. Like if the 2 things are independent, we know that this will equal 0. And so that's just the same as saying like v of ax plus by. This is kind of like how we did in the other video, right? We can break that up. So we're saying we're assuming this is independent, a and b in this case. We can break that up. Plus v of by, and then we can pull the constants out. A squared vx plus b squared by. And that would just equal that. And so if they're independent, like this, a squared bx plus b squared by, it's the exact same thing, like if we just kind of broke it up and did that and then squared it like we did. And so that's kind of nice, but if they're not independent, then we're gonna have to add that guy on. So if you guys want, I just wrote like a quick practice problem. We can calculate this real quick. If you want, you can pause the video and do it. If not, you don't really have to, but let's just go through this real quick. You can do it if you want, but I mean, it's pretty easy, I guess. So we would just, the constant, the a and b, that's just our 3 and 4, right? So we just have 3 squared times v of x times 10 plus b squared, that's, what's that, 4? Plus 4 squared, v of I, that's 5. Plus 2 times a times b, covariance of x, y, 20. So what do we get from that? We get 90 plus, oh gee, I don't even remember. Okay, that's 16 times 5. We can go back to that. I think that's 80, yeah. Yeah. Plus, let's see, plus that's what, 6, that's 24. Should have brought my calculator, but oh well. 48, 480, I hope that's right. So then we add all those up. Let's see, we got 170 plus that is 580, 650, I think. I think that's right. Hope I did the math right. I guess I'll have to double check that. But yeah, that's just that equation. So definitely learn that equation for the exam. But yeah, so sorry about those errors.